Hello everyone and welcome back to my channel. If you haven't subscribed to my channel yet, please click the subscribe button and the bell button for notifications. In our previous video, we have discussed about multiplication and division of decimals. If you haven't watched that video, please click suggested video above. For this video, our lesson is all about principal roots and its nature, whether it's rational or irrational. Before we talk about rational and irrational numbers, let us first discuss about real numbers. The real numbers is the set of numbers containing all the rational numbers and all the irrational numbers. The real numbers are all the numbers on the number line. There are infinitely many real numbers, which means that a rational number is a real number and an irrational number is also a real number. Under the rational numbers, first we have whole numbers. Whole numbers are 0, 1, 2, 3, and so on. Next, we have integers. Integers includes whole numbers as well, and also our negative numbers, -1, -2, -3, and so on. These previous two sets are called rational numbers. Along with them are fractions. Fractions are defined as rational numbers because it can be expressed as a ratio of two numbers, that is the ratio of 1 and 2. A fraction is a rational number. A terminating non-repeating decimal. 125 thousandths is an example of terminating non-repeating decimal, which can also be expressed as a fraction. In fraction, that is 1/8. Therefore, it can be expressed as a ratio of two integers, the ratio of 1 and 8. Therefore, it is a rational number. And lastly, we have non-terminating repeating decimals. When we say non-terminating, it will not stop. Repeating means the same number repeats. In this case, the number 3. It can also be expressed as a fraction, that is 1/3. Therefore, it is a ratio of two integers. It is also rational. But what about our irrational numbers? An example of irrational number is pi. Pi is equal to 3.141592 and so on. We cannot predict the next numbers because they are not going to terminate and they are not going to repeat. Also, the Euler's number is 2.718281 and so on, and we cannot identify the next numbers because they are non-terminating and non-repeating decimals. Only non-terminating, non-repeating decimals are irrational numbers. To sum it up, rational numbers are those numbers which can be expressed as a ratio between two integers. These are numbers that can be expressed in the form a over b, where a and b are integers and b is not equal to 0. For irrational numbers, those are numbers which cannot be expressed as a ratio between two integers. These are numbers which cannot be expressed as a quotient of two integers. Let's have the basic parts of a radical. This is called the radical sign. The number inside the radical sign is called radicand. And the combination of the radical sign and the radicand is called a radical. Next is about the perfect square and the principal root. The square root of 36. 36 is a perfect square. Perfect square is a square of a rational number. We can identify a number if it is a perfect square if there is a number multiplied by itself and gives 36. And what is that number? That is 6. 6 multiplied by itself, 6 multiplied by 6 is equal to 36. Now 36 is a perfect square. 6 is the principal root of 36. A principal root is a number which produces a specific quantity when multiplied by itself. It is the positive nth root of a number. The principal root of 36 is equal to 6. To better understand perfect square and principal root, let us illustrate the numbers. If you have studied about area of polygons or specifically area of a square in your earlier grades, this is a very relatable topic. Can you remember the formula for area? The formula of the area of a square is equal to s squared, where s is a side because all sides of a square have equal measurement. Let's have the smallest perfect square that we can make. That is 1 square. Each side of this square measures 1 unit. 1 is a perfect square. And its multiplication form is 1 multiplied by 1 gives us 1, and our exponential form, 1 squared, is equal to 1. Now our principal root is 1. And in radical form, we have the square root of 1 is equal to 1 because 1 multiplied by itself gives us 1. Let's have the next size of the square. How many squares can we find in the illustration? We can find 4 squares. The area is 4. Now it means that 4 makes a perfect square. Let's have multiplication form. How many units does each side of the square measure? That is 2 units. 2 multiplied by 2 is equal to 4. And our exponential form, 2 squared, is equal to 4. Therefore, the principal root of the square root of 4 is equal to 2. In radical form, square root of 4 is equal to 2. For our next square, we have 3 units on one side, which is the same exact measurement for all sides because we are looking for a perfect square. Let us now count how many squares can we find. We have 9 squares. Now 9 is a perfect square. Its multiplication form, 3 multiplied by 3, and in exponential form, we have 3 squared. Therefore, our principal root is 3. In radical form, the square root of 9 is equal to 3. Now we can find 16 small squares making up a perfect square. 16 is a perfect square. Its multiplication form is 4 multiplied by 4, and in exponential form, we have 4 squared. Therefore, the principal root is 4. In radical form, we have the square root of 16 is equal to 4. In this figure, we can find 25 squares, and it makes a perfect square. In multiplication form, we have 5 multiplied by 5. In exponential form is 5 squared. The principal root is 5. Now in radical form, we have the square root of 25 is equal to 5. Adding more squares, we have 6 units per side, and we all have 36 small squares. Now 36 makes a perfect square. In multiplication form, 6 multiplied by 6 in exponential form is 6 squared. The principal root is 6. In radical form, the square root of 36 is equal to 6. Let's add some more squares. That makes one side equal to 7 units. Now think of the formula of the area of a square. 7 multiplied by 7 gives us, that is correct, 49 is a perfect square. In multiplication form, 7 multiplied by 7, exponential form is 7 squared, and our principal root is 7. Therefore, in radical form, we have the square root of 49 is equal to 7. If we count the number of squares, we all have 64 squares because 64 is a perfect square. In multiplication form, we have 8 multiplied by 8 in exponential form, 8 squared. Principal root is 8. Now the radical form is square root of 64 and its principal root is equal to 8. Adding more squares, we have 9 units per side. 9 multiplied by 9 gives us 81. Its multiplication form is 9 multiplied by 9. Its exponential form is 9 squared. And the principal root is 9. Therefore, in radical form and principal root, we have the square root of 81 is equal to 9. And lastly, we all have 100 small squares that also makes a perfect square. Now 100 is a perfect square. In multiplication form, we have 10 multiplied by 10. In exponential form, we have 10 squared. The principal root is 10, and in radical form, the square root of 100 is equal to 10.
Please click the subscribe button and bell button for notifications. Thank you.
I hope that you have better understood about perfect squares and its principal roots. So let's review our previous examples. The radical form is the square root of 1. The principal root is 1. The radical form is the square root of 4. The principal root is 2. The square root of 9 is equal to 3. The square root of 16 is equal to 4. And the square root of 25 is equal to 5. But what if we have the square root of 2? 2 does not make a perfect square. Now its principal root is hard to calculate just using the original calculation method. If you're going to use the calculator, you can find it fast, but it gives us 1.4142 and so on. Another example is the square root of 7. 7 does not make a perfect square, and its principal root is 2.6458 and so on. The square root of 11. 11 is not a perfect square. Its square root is 3.3166 and so on. The square root of 24, since 24 is not a perfect square, its square root is not a whole number as well. That is 4.899 and so on. The square root of 30. 30 is not a perfect square, so its principal root is not a whole number. It's 5.4772 and so on. If you have noticed the examples in the table colored orange, all the principal roots are whole numbers. On the right side, we have the table that is colored yellow. Principal roots are numbers with decimals and ellipses. It means it will still go on and on. Now let's differentiate those two different examples. The left side are rational numbers and the right side are irrational numbers. How can we identify if the given radical is a rational number? First, is the principal root a whole number or fraction? If your answer is yes, then it is rational. For irrational, the principal root is a non-terminating, non-repeating decimal number. Remember, in the square root of 36, the principal root is 6. Now the square root of 36, of course, is rational. Another thing to identify that the radical is a rational number if the radicand is a perfect square. The radicand is the number inside the radical sign. Example, square root of 100. 100 makes a perfect square. Therefore, the square root of 100 is rational. For irrational numbers, check if the radicand is not a perfect square. If it is not a perfect square, therefore, it is irrational. Let's have examples of rational numbers. The square root of 36 is rational because it is equal to 6 and it is a whole number. The radicand is 36. 36 is a perfect square. Another example is a fraction. The square root of 49 over 64. To identify if the radical example is a fraction, either if it's rational or irrational, you check if the numerator is a perfect square, and if the denominator is a perfect square, then it will be rational. In this example, 49 is a perfect square, and 64 is a perfect square. We have our principal root. The square root of 49 over 64 is equal to 7 over 8, therefore rational. And our final example is the square root of 100. Since 100 is a perfect square and its principal root is equal to 10, which is a whole number, therefore the square root of 100 is rational. Let's have examples for irrational numbers. The square root of 39. First, the radicand is not a perfect square, therefore it is irrational. The square root of 1/7. Check. The numerator is a perfect square, but the denominator is not a perfect square. Therefore, the square root of 1/7 is not rational or irrational. And the square root of 98. Since 98 is not a perfect square, it means that the square root of 98 is irrational. Let's try some more examples. We have the radical, the square root of 49. Now for our first requirement, it should have a principal root that is a whole number or fraction. Think of a number multiplied by itself gives 49 to find the principal root. And there is a number. The number is 7. 7 is the principal root of the square root of 49. 7 multiplied by 7 gives us 49. And check if the radicand is a perfect square. And 49 is a perfect square. Now it means the square root of 49 is rational. Another example, the square root of 3. The principal root of a square root of 3 is 1.7321 and so on. It is not a whole number and it cannot be expressed as a fraction. Its radicand is 3 and it is not a perfect square. Now we know that the square root of 3 is irrational. Our third example is the square root of 50. Can you think of a number multiplied by itself that gives us 50? Since we cannot think of a number, the answer, square root of 50, is irrational. Another example is the square root of 26. The square root of 26. Check its radicand. Is it a perfect square? 26 is not a perfect square, therefore irrational. The square root of 81. Since 81 is a perfect square and its principal root is 9 and 9 is a whole number, now the square root of 81 is rational. Let's have some more examples. The square root of 121. Now, when the numbers go big, my advice for you is you try to memorize at least from 1 multiplied by 1 up to 20 multiplied by 20. Because if you already memorize that, you will identify that 121 has a principal root that is a whole number, and that is 11. 11 multiplied by 11 gives us 121, which means 121 is a perfect square. Now the square root of 121 is rational. The square root of 25 over 64. Now for a fraction, you have to check if the numerator is a perfect square and if the denominator is a perfect square. And for this example, 25 is a perfect square, 64 is also a perfect square. Now it has a principal root that is a fraction, and that is 5/8. Now the square root of 25/64 is rational. Another example, we have the square root of 12. The square root of 12 has a principal root of 3.4641 and so on. Its radicand is not a perfect square, therefore it is irrational. Next example, we have the square root of 144. Again, if you have memorized the table, you can identify that 12 multiplied by itself is equal to 144, which makes 144 a perfect square, and the square root of 144 is rational. For our last example, we have the square root of 6/21. 6 is not a perfect square, and 21 is also not a perfect square. Its principal root is 0.2857 and so on. It is not a perfect square, therefore it is irrational. And that ends our lesson in principal roots and its nature. I hope you have understood the lesson well. If you have any questions, you can comment it down. For my next video, we are going to talk about determining or estimating which two consecutive integers the irrational number lies, or estimating which part of the whole number. Stay tuned and thank you for watching.